So I'll see every laptop down, or at least not being viewed. So that put it in a position where you can view it and you get distracted off. Rather you're doing the EP. But the two reasons, number one, the only reason we started with yesterday's work was so that we could, I guess we're more rules focused, whereas today is really about understanding why are we deriving, why are we doing this process repeatedly, and where can it apply. And one of the clear spots that applies is curve sketching. Now we've done a bit of curve sketching before. It's probably the most time consuming part of your exam in the first one. But knowing the direction of the rate of change really allows us to do it a lot more quickly and a lot more easily with a lot more certainty about what we're sketching. Okay. It's very similar to the process. The only thing that changes is that we need to use our derivative. And with our derivative we find all our stationary points first, and then we pick some values to the left or the right so we know what's happening between. So when we look at these stationary points, like if you sketch a function, sketch any function you like on your page, it's got to have more than one stationary point. Just sketch a random function on your page with more than one, doesn't have to be accurate, just a shape, just a random shape. Whatever function you choose to draw, I don't care what it is. It could be a trig function, cubic, quartic, fiftic, whatever they call those things, ninetics, I don't know. I don't care how many turning points it's got, you pick me a random as long as it's a function. So how do we know it's a function? Only one y value for every x value. So let's say you drew a funky dunky wonky donkey that looks something like this. I don't care what it is, right? Even have a point of inflection for all I care. I want you to circle all your stationary points. So for me, I'd have one there. Doesn't matter, right? Now you need a ruler or a pen or something straight. God forbid if your fingers aren't too broken, you could probably use one of them. And what you're going to do is just trace your tangents as you go around. Okay? So if I was doing it, I'm not going to use my finger because I want it to be obvious, but I would start with, is that tangent negative or positive? Negative. How can you tell? Yeah, so we should be seeing that downward slope. If it's a positive, it should be an upward slope. Cool. Think about walking a hill. If we're walking forward, we'd much rather walk downhill than uphill. So every time we get to a stationary point, I want you to identify what happens here. Okay, so we're going do. Okay. So what's happening at every stationary point?
Flips.
It's changing, right? Is every stationary point on my diagram going to do that?
No.
Which one? Point of inflection. But what's going to happen, right? It's going to go positive. Assume I could draw a point of inflection properly. It's going to go positive, 0, positive, correct? We can deal with that. But the other question I'm going to ask is, between any point, any stationary point, does my tangent ever go from positive to negative? My tangent always stays. So if I start here and go to there, I know that it's positive the whole way through, correct? Between these two, I know that it's negative the whole way through. Between these two, I know it's positive the whole way through. And that's important for what we're about to do, because what I'm saying is, if I've got, I need to know where my stationary points are, right? But I can pick any point along that line and it will tell me about the direction of the tangent, correct? So I can pick any point and do what with it? What do you reckon I can do with any point along that line? Sub it into what?
Function.
What function? Derivative function. And if my answer is negative, what's it tell me about the tangent the whole way through?
It's negative.
It's pointing down. If it's positive, it tells me the tangent the whole way through is pointing up. Makes it a lot easier to sketch, right? So we're going to go through an example of how that works. Here we've got our function y equals x cubed minus 3x squared plus 4. We need to curve sketch. Now I've done the first part pretty briefly because we know how to do that. We've done that to death, correct? Y-intercepts, x-intercepts. In this situation, we'd have to use long division to find it, but I'm just going to give you your x and your y-intercepts because this is not about that part of the curve sketching. This is about the new skills that we've learned and how we can increase our accuracy and make it a lot quicker. So once I've got my intercepts, I sort of keep a note on them. Like if I was actually doing this problem for myself, what I'd be doing is going, well, I know my function is going to be approximately in like this shape here, correct?
Yes.
I know I've got an x-intercept here and an x-intercept there, and I've got a y-intercept up here. So I've already marked out those points. This point here is 4, this point here is, what did I say, 2, and this point here is -1. Sweet? I know it goes through all of those points. But what I don't know is what's the direction. I've probably got an idea because I'm dealing with a positive cubic and I've done enough of those. Like I probably know that it's going to keep charging off in this direction and it's going to do this, but I don't know where the stationary points are, etc, etc. So what I need to do firstly is derive this function and identify where my stationary points occur. So I derive it. How do I know if I've got a stationary point? What do I do?
F dash x equals 0.
Yep, let my derivative function equal 0 and then solve for x. I get two derivatives, 2 points where my derivative function is 0. At x equals 0 and x equals 2. Well, geez, isn't that convenient? Why is that such a convenient thing?
Because it's going to be at the intercepts then.
I already know those 2 points, correct? I already know that I've got, that's one of those points. So I know that I've got a turning point here. And one here. Cool. What I don't know is the direction of the function outside of those points. So to do that, I create a table. Now I've got to have a point to the left and to the right of every turning point. So how many points do I need outside? So I need a point before 0, I need a point with bigger than 0 but less than 2, and I need a point bigger than 2.
1 and 3.
Pick some values for me. What's a number that's less than 0?
-1.
Negative 1. Can I use negative 1?
Sure.
Can I use negative 2? Can I use negative 3, negative 4, negative 0.3? I can use whatever I like. Why would I use negative 1?
Because it's in the thing.
Because we're lazy and it's easy. And it's already on the thing, but that doesn't matter. What point should I pick between 0 and 2? 1. Why? Because we're lazy and it's easy. And it's probably a tech-free question. What about bigger than 2? Geez, we're good. Now, I've got 0 here. This is all about the gradient of the derivative function. So where should I put these values in? Into what function? My derivative function. I don't need to do a heap of maths here, right? 3 times 1 squared is?
3.
Minus 6 times 1? No, positive 3 minus 6, which is? Do I care that it's negative 3? It doesn't matter if it's negative 3, negative 4, negative 15.7. What do I care? I care that it's negative. And I'll show you why. Negative 1 squared.
1.
Positive 1. Positive 1 times 3 is?
3.
Negative 6 times negative 1?
6.
Positive 6. So positive 6 plus positive 3? Do I care that it's positive 9? I just care that it's positive. 3 times, well, 3 squared times 3?
27.
Minus 6 times 3?
18.
Do I care about the value? What do I need to know?
Positive.
That it's positive. Which one's bigger, 27 or 18?
27.
So I know it's going to be positive. And I can see some people in the room going, yeah, but why is that going to help me sketching? I don't need to do, and I'm going to make I want you underneath, hopefully in your book you've got more space underneath your table, right? I'm going to rub this 3 out. Have we all written that down? Just write that part down quickly so I can rub out the part above it because it needs to be joined to the table. So I'll give you 10 seconds to write down, create a table with f dash x versus x. I don't need brackets there, that's just confusing. It's bad board work. It doesn't matter which function is on top, whether it's f dash x or x, it's not for that. Okay. So, are we all good? And rub out some stuff now?
Run that table.
Yeah, I'm not going to rub the table out and rub it, yeah, above it, but that's okay. So I'm just going to rub this part of it out. Okay? Now the reason I'm rubbing that part out is because this diagram needs to be with the table. Can you all give me a positive gradient? Show me what a positive gradient looks like with your arm. Every person in the room is doing this. Correct?
I'm doing that.
Show me what a flat gradient, a 0 gradient looks like. Show me what a negative gradient looks like. Show me what a 0 gradient looks like.
Same as that one.
and positive. So I know my function's going to be doing that, correct? So now I just take all the information that I have and I put it together. Well, I know it's going to intercept at 4. I know there's a turning point here. I know it goes through this point here, so I know that my function's going to look like that. That's that part done. Sorry? Yes, it is. That's positive. Good.
How do you know it went through negative 1 here?
Up here. Cool. I wrote that out before, sorry. I know that it goes through the point 2 and it has a turning point there, correct? But I know that every point between 0 and 2, like everything in here, is going to have a negative gradient, correct? And I know that it turns at that point there, and then what does it do after that? Ta-da. Curve sketching.
That looks pretty good.
It's the ugliest looking cubic function you're ever going to see. But it's got all my key features. It's got turning points where it needs to have them. It's got intercepts where it needs to have them. It's the right shape. And I've proved that I've got my tangents going in the right direction. Awesome. Are we happy with that?
That's pretty awesome.
So this part 1's the same. 2, we're really comfortable with 2. Just be aware with 2, if I didn't have these points already, so if I didn't know that already, what would I have to do at this point here? I'd have to sub these values back into my y function to get my coordinates for my turning point. Cool? And then I use my table and I sketch from there.
Lovely.
Happy with that? So this is the why we do it, the chain rule, so that's the how we do it. So when we learn all the derivative rules, this is why we're doing all of this stuff. So we can use the rate of change to help us with our mathematics, and that's just one of the applications.